Hello, everybody. I am Sofia, and I will introduce our paper, Your Image is My Video. What we do in this work is proposing a new auto-augmentation technique named Differentiable Augmentation Search to generate variation of images that can be processed as a video. We then use this DAS to guide the reshape of the spatial receptive field of CNNs for the task of image classification and semantic segmentation. So, since the creation of AlexNet, creating models with significant increased capacity has been the prevailing approach in designing CNNs. Despite the success, these high-capacity models necessitate increased computational resources and strong regularization due to the over-parametrization. One way of regularizing network is employing data augmentation techniques, which are easy to use, but most of the time necessitate domain-specific knowledge. Now, for datasets like Cipher10, ImageNet, and MNIST, we already know which transformations to apply. But given your new private dataset, this is not trivial. And to this aim, inspired by neural architecture search, various auto data augmentation methods were born. Now, our approach consists of two components. We have a temporal expansion, where we transform an image into a fake video, and a new auto-augmentation technique to properly do that. So we generate a series of images that exhibit motion, as I said, and treat them like a video. Why do we do this temporal expansion? Because we thought that an increased receptive field in the temporal dimension could lead benefit also to the spatial one if the generated video is obtained through a proper set of transformations and the features of adjacent frames are properly mixed. This leads to our method that, differently from others, reshapes the receptive field and does not only expand it. Our second component is the DAS method. And second question, why an auto-augmentation method and why differentiable? Well, the need for auto-augmentation, I guess, can be better caught by this image. If you move the gecko randomly, you will probably mix, well, when performing the convolution on the temporal component, you will mix random features that do not help you. And why a differentiable approach? Because many of existing approaches either require much time, as auto-augment, forcing the search to be performed on a proxy task, or do not propose an effective search strategy, but rather propose a well-defined search space, as in random-augment. As a result, as we empirically show, including noisy transformation would imply much larger searching time to achieve the same performance. So in a nutshell, you can reshape the receptive field also with auto-augment and round-augment. But auto-augment is slow, and round-augment needs you to have a priori knowledge for the transformations to include. How does this thus work? Well, we define a continuous search space of transformations, which implies that the categorical choice of applying a transformation is relaxed to a softmax of all possible ones, as you can see from the formula. Then, having this differentiable formulation allows you to optimize both the tau value and the weight of the network in the B-level optimization problem through gradient descent. At the end of the search phase, the best transformations are chosen by deploying a perturbation-based approach, where the transformation importance is evaluated in terms of its contribution to the neural network performance. To this aim, we mask one transformation at a time, reevaluate the network, and see what operation results in the greatest accuracy reduction. The flow of the whole method works like this. An input image is processed through a DAS cell. The cell applies all possible defined transformations and generates an input video. The video is processed through a video network integrated by a temporal-shift mechanism with the goal of shifting the features of adjacent frames. I would like to point out that although a general video network can process the video input, to reduce the complexity and keep efficiency in our task of interest, we deploy a 2D backbone with a temporal shift mechanism called GSF. For each insert in GSF, the temporal receptive field will be enlarged by 2, and part of the features among 3 adjacent frames will be mixed. As the content in the adjacent frames is nothing but the same image, either translated, scaled, or rotated, the increase in size in the temporal receptive field can be mapped in an augmentation in size and reshape of the spatial receptive field. Finally, the prediction for the video input are combined so that the performance for the original 2D task are given back as feedback to the DAS cell. For the results, I decided not to put huge tables nor the boring ablations, but just few key concepts and main characteristics I would like you to keep from this approach. For ImageNet, what we mainly experience is a reshape of the receptive field, as you can see from the figure, where we compare how the receptive field looks like with a standard 2D CNN and with the same CNN but used with our approach. And then we experienced, as the plot highlight, a less steep performance degradation when reducing the depth of the network. So a side note, the original name of the paper was Go Wide and Not Deep, as the original idea was that if we were able to expand the receptive field by generating variations of the image, we would have probably needed less deep networks. And it's cool because it's what we experienced, what we saw in this plot, and what you can also appreciate from the numbers. For semantic segmentation, what we experience both for Pascal and cityscapes from the qualitative point of view is a better capability in segmenting details. This is clearly visible, especially for people segmentation, as you can see, and for street lamps, as you can see on the third and fourth row. That's it. Thank you for your attention.